Hey everybody, welcome back. Mr. Smith here. In the last slide deck, we introduced the idea of energy and talked about how access to energy has radically changed life for the better for the people of the world. Right now, our world is in the middle of change from fossil fuel energy and other kinds to more renewable types of energy. And that discussion is going to take place for us over a period of the second half of the school year. So what we're going to do in this slide deck is zero in on one thing that's very important to physics, and that's mechanical work. So over on the right-hand side of this little energy web, you're going to notice a couple of terms you've probably seen before: kinetic energy and potential energy. So kinetic is energy of motion, potential is stored energy or energy of position. And we're going to talk in the coming weeks about how work is any kind of transition from one kind of energy to another. So that'll be a topic for another day. But what we're going to do right now is zero in on mechanical work. So that's work that's big, physical, it involves moving objects. And to do this, we're going to get started with a car. So couldn't get any more basic than that. Even if it's an F1 car, it's still a car. So what we have here is our first formula. Work equals force times distance. So if we have a force and we have a distance, we're going to have work done with one catch. The force and the distance need to line up with each other. So when they do that, we're going to get what's called positive work. So check out our example. Red Bull F1 car accelerated from rest by 8,000 newtons of force. So I can visualize this car speeding up because there's a force pushing on it. So I draw a force arrow on it and it's pushing to the right. Also, you can read the question and see that the distance is to the right. And so what have I got? A force that's positive, a distance that's positive, and that's the recipe for making positive work. So it's pretty straightforward. Work equals force times distance, and we just pencil them in. So 10, that's the next example. 8,000 newtons of force times 94.5 meters of motion, and that gives us a great big amount of work that was done. 756,000 joules is our unit for newtons times meters, and that is spelled Joule. It's named after an English guy who did the first conservation of energy experiments, which we'll talk about later. But anyway, there you go. Work equals force times distance. Force and distance line up, you get positive work. Okay? Check out this example. Cars don't just speed up, they also slow down. So right now what I'm imagining is this car is traveling along at some big rate of speed going this direction, and to slow it down, it applies a braking force. Well, look what I did. To slow this car down, we're going to need a force that pulls against the motion of the car. That's going to be a negative force. And the car continues forward because of inertia. That's the distance right there. And so when I do work equals force times distance, I still get work, but check it out. It's not going to be positive work. What I get is a negative 10,000 Newton force, and that's going to multiply into a positive 30 meters, and you can see easily how that produces negative work, negative 300,000 Newton meters, or negative 300,000 joules of work. So again, if force and distance are opposite each other, you get work, but it's negative. Okay, and now what we're going to do is turn our attention to lifting work, and to do that, we're going to turn to Ray Williams, one of the biggest men I've ever seen. So take it away, Ray.
Ray versus Fedoshenko, U.S. versus Russia, 398.5 on the bar for the Champion of Champions Award. Whoa! Fast!
Wow, that was fast.
I think he might have done it!
I think he has.
Okay, so the man definitely did work. Why? Because there was a force involved. It was a lifting force. It went vertically. The weights moved vertically. So we had force and distance line up with each other. Work got done. But in lifting work, there's one extra step you want to remember, and here it is, that if you are holding, not even lifting, just holding a 398.5 kilogram mass, the force that you exert on it has to be upward, and it has to equal the weight of the thing. So what you want to do is go back into the force unit and just remember that formula. Weight equals mg. So here's how it operated. Remember, weight for this mass would be equal to negative 3,985 newtons. So the up force is what we're interested in here. That's what Ray is doing to the weight. That's going to be the same number, 3,985 newtons going upward. Here's the thing. If he lifts these, which he does, at constant velocity, this number is the number we're after. The lifting force doesn't have to be bigger than the weight during the lift. He just has to win the tug of war for a second just to get those weights moving, and then he pulls them up by exerting this force. Okay? So what we've got, a force, 3,985 newtons, a distance moving upward of 0.93 meters, and we can go to work on that. So work equals force times distance. I've got my numbers now, 3,985 in the positive direction, 0.93 meters in the positive direction. And what I'm going to get is positive work. So I multiply all that, I get 3,706 Newton meters or joules. So force and distance lined up. Ray Williams did positive work. Check out the next one. So in this one, you can see that Ray holds the weights 93 centimeters off the ground for a second, and they're asking us how much work does he do simply by holding the weights there in the middle of his lift. So here's the thing I want you to know. It definitely is not easy to do this. So Ray is holding that 398.5 kilogram mass. He still has to apply the same exact force, 3,985 newtons upward, in order to hold it. But the catch is that the distance here equals 0. If Ray is just holding the weights above the ground, the distance in the motion isn't anything, and this should bother you. The work is going to be 3,985 newtons times 0 meters, and you know what that's going to equal? It's going to equal 0 joules of work. Here's the thing. What we're going to do right now is make sure you understand there's a difference between work being done on the object and work being done inside your own body. Is it hard to hold a heavy thing and keep it steady? You bet. Does your heart work harder? Yeah, absolutely. Do your muscles strain and do work inside of your own body? Yes, they do, at a very micro level, and it's not easy. But in terms of work that's being done on the weights themselves, he doesn't move them, he doesn't speed them up, and so the work that he does is actually 0. Now, the final phase of the lift happens when Ray lowers these weights to the floor, and the question says, how much work does he do as he lowers them? There's a common sense thing here I want you to pick up on. This is 398.5 kilograms worth of mass. By themselves, they would plummet to the floor. So if Ray doesn't actually support them by lifting upwards, they're going to free fall. That's not what happens. He lowers them under control. So the thing I want you to recognize is a little weird, and you may want to ask about this in class, is that he has to apply the same exact force upwards in lowering these weights at steady speed as he did to lift them at steady speed. And that is a phenomenal example, actually, of inertia. So 398.5 newtons is the upward force that Ray has to exert even as the distance is going downward. And so downward distance, we know what that is. That's going to be negative 0.93 meters. And you can see this coming. The math is pretty straightforward. Again, work equals FD. This looks like this is going to come out to be negative of the example we just did a minute ago, right? 3,985 newtons is positive. Distance is negative 0.93 meters. And this is going to turn out to be negative 3706 joules. So that's the negative of the lift. So one last example and we'll bring it on home. So a second formula that we're going to deal with is this one right here. It's very straightforward to use. Think about this. They don't call this powerlifting for nothing. So powerlifting is all about doing a huge amount of work in a really short amount of time, usually. And so what they give us is this second formula, power equals work divided by time, and we'll just put it to use here. So we know that in the positive of the lift, Ray did 3706 joules worth of work. And they tell us that the time that it took him to do this was 2 seconds. We just kind of made that up. And what we're going to do is just go and get power equals work over time. and to go and plug them in and divide. So 3706 joules, 2 seconds, and I think the unit is going to make sense when you see it. So I divide those and I get 1853 joules per second is how quickly you do the work, and that is called watts of power. So yeah, if you've ever heard of watts in a light bulb, that's the same thing. Watts of power. This is a lot of light bulbs this guy could be lighting if he could do this all day. Anyway, that's the basics. So work equals force times distance when they line up. Power equals work over time. You might have some questions. I hope you wrote them down. Bring your questions to class though, and we'll see you soon. Take care and have a great day. Bye-bye.